Hi, and let's think about where these things came from and think about what goes on. Your teacher might have told you about a thing called an isotope. I know you've learnt about atoms, and we know that atoms are basically made of protons, neutrons and electrons, and that's been in the making for many hundreds of years. And in some other videos you might have seen how I've gone through and told you what's in an atom and who did the work with it. So let's continue on that vein and let's see what's going on in terms of isotopes. Probably the most famous isotope is this one up here, carbon-14. And scientists use it to date dead things. It must have been a form of a live thing, and they can actually tell us approximately how old things are or how long ago they died. Now, some of these terms up on this side you would have seen before, how we've got the element symbol here. Just put a generic X here. We have a raised number, and that is called the mass number. It will be the larger of the two. And the bottom one is the number of protons or the atomic number. So all these things should be fresh in our mind. Now let's use that and let's see what actually happened. Alright, in previous videos we know that this is the generic model of the atom, but it's not correct, is it? Because we don't have the little racetracks for the electrons to move around on. We used to call them orbitals, and that's why they're drawn like this. Like the moon orbits us and we orbit the sun. So we say that they go around the nucleus. But now we're finding out that this pattern is more like a cloud. So it's less rigid in its structure. It's a bit more flexible and allows certain things to happen. More about that when we get on to electrons. Alright, so the next question came up. For millions or for thousands of years we've been thinking that atoms are the same. So we've been teaching that, and it was taught for a heck of a long time that all the atoms were identical. And John Dalton did a lot of work on this about 300 years ago. He did a lot of work on it. He came up with some good ideas. Some not so good ideas that Mr. Dalton came up with was the fact that he said that all atoms are indestructible. And of course we know we've had the splitting of the atom to make the atom bomb, so maybe his ideas weren't correct. But you've got to realise that his technology was not very good at the time, nowhere near as good as what we have now. Now, scientists use his ideas, and other scientists came through, a fellow by the name of Soddy, and we've already seen what Mr. Rutherford has done. And he sort of said that the atom has parts to it. Remember, he said the positive nucleus and the electrons move around because electrons had been discovered, or if you like, or identified by a fellow by the name of Thomson. So we came to the idea that different atoms could exist, and it had to be due to what was inside them, and that was when the name isotope came on. One of the keys to this was the fact that if everyone was concentrating on charged particles, we knew an electron had a negative charge and would bend towards a positive electric plate or react a particular way in a magnetic field. Same. Now, they also knew that positive particles would do the same. They would act a particular way when coming in contact with a positive or negative electric plate or a magnetic field. And so people concentrated on the positive and negative. They didn't think the fact that perhaps some of the parts of the atom were neutral or didn't have a charge. And it wasn't until this fellow, Mr. Chadwick, came along, no relation to Mrs. Chadwick, and he came along and he was working with what they actually call them with canal rays. In other words, they were beams of electrons. And he found that there was a neutrally charged particle. In other words, it wasn't affected by magnetic or electric force fields. And he christened that the neutron. And the only place it could have come from was the atoms. So he deduced that a neutrally charged particle was also present in the atom. So, Mr. Soddy at the same time had been going through and working out all these different atoms that had isotopes. Now we actually find these days most atoms have isotopes. The naturally occurring ones definitely have isotopes. For example, if we are looking at number 1 on the hit parade, our good friend hydrogen, hydrogen has 1, 2 and 3 isotopes. Now each of those isotopes has something different about them. This, the top one, hydrogen 1, is the usual stuff. So this is stuff we find makes up in water and things like that, and we found in us. A little bit of this is around, hydrogen 2. It was used in making the atomic bomb. And this stuff is normally associated with nuclear reactors. The only trouble is it's extremely lethal to us. And they gave them old-fashioned names. Hydrogen 1 kept its name. If there were 2 protons in the hydrogen, or a proton and a neutron, we actually called it deuterium. Deut as in duo, so as in 2. And the one with 3 was called tritium. Tri, like a tricycle, tripod, 3. And so this came with it. Now, this was going quite well, and then another dude came along and he made a measurement. He made a device that was able to measure it. And we still use this device today. And it's called a mass spectrometer. And what it does is it uses electric and magnetic fields to spread the different isotopes of particular elements out so we can count them. Now, the fact that we've done this means that when we see hydrogen, for example, in the periodic table, we might see that. And that is a reflection, this number here, the 1008, is a reflection of the average mass of all the different isotopes. So we couldn't have done it without Mr. Aston and his mass spectrometer. So we've worked this one out, and he was able to do it. So what does a mass spectrometer look like? Well, most of the time it's in a box. And what we do is we put a sample of, let's say we put a sample of gold in there. And it goes in this end, and it says vaporise. In other words, we have to turn it into a gas. So we heat it, and we turn this small sample of gold into a gas. I'm going to use gold all the way through. Right, it comes in here. Then these plates along here are designed to make the gold charged. Ionise means to give it a charge. Normally we give it a charge of a positive charge, and normally it's a positive 1. So the gold comes in here, it becomes gold 1. So if you like, we start off with Au. Here we come Au plus. Then what we do is we put it through a magnetic and electric fields. And what that does is it moves the path of these isotopes they're going to follow based upon how big they are. Their charge to mass ratio. In other words, how big. Right, so if they've got so many particles inside, they will bend a particular amount. If they've got more particles, they'll bend a different amount. Or less particles, they'll bend a different amount again. So all the different isotopes are bent here. Now this part here is your collector. And what it does is then sends a message. It uses a really fancy machine which converts the number of hits into a electric current, and that goes onto your monitor. So the more there is, the bigger the current, and that transposes to a bigger peak, as we're going to see in a minute. Alright, so we don't really have to know this. If you go and do diploma chemistry, you might be spending a little bit of time with a mass spectrometer, or as in finding out about it. But at stage of 10 and 11, I don't think there's that great a deal for us to worry about it, or even below that, there's not much to worry about. All you've got to realise is that we put the atoms in, they become ions. The ions then are moved through magnetic and electric fields, and where they land is converted into electric charge or electricity, and that is displayed on a monitor. It's sort of like magic. So when they come out, it looks something like this. Now, I've already mentioned the fact that everything has isotopes, and I gave you the example of hydrogen, 1, 2 and 3. Oxygen has it, carbon has it. And as I said before, we've got, when we had our basic carbon that makes most of us, it's that one there. But we also have a little bit of that inside of us. And when we pass away, this one is what we call radioactive, so it's going to decay. And that's another story. But let's just say it gradually will disappear. And as it disappears, it releases radiation. So if we know how much it is, we can work it back and find out how much was in it when the animal was alive, and from that we can work out how long ago it lived. And that's carbon-12 dating. Now this one is of Krypton. This thing here is a charge to mass. So at 80, we have, let's say for Krypton, we have one isotope here, number 78. One isotope here, number 80. But there is more of number 80 than 78. I can tell because the peak is bigger. Then we go to number 82. Then 83. The main amount of, or the most common form of Krypton is 84. I can tell that because it's got the biggest peak. And then of course we come down to another one is 86. So we can see that Krypton has 1, 2, 3, 4, 5, 6 different isotopes. And then if we average those out, we would get the value of the atomic mass of Krypton. And you can look that up on your periodic table. Right, that is an introduction to isotopes.